Hello again. Alright, in this second video we're going to talk about the inverse trig functions. Alright, now we're not going to go into super depth about the domain restrictions that are appropriate to make these well defined. Right, but over appropriate intervals the functions cosine, sine, and tangent each have inverse functions. They are denoted using special notation. Alright, inverse cosine is written this way, inverse sine is written this way, inverse tangent is written that way. Alright, and the main thing we want to know about those is that, again, inverse functions return the outputs back to the inputs. Well, if the original functions take in angles and output numbers or ratios, if we want to think about that, think about the right triangle interpretation of trig functions, then again, the original functions input angles and return numbers or ratios. The inverse functions are therefore going to do the opposite. They're going to take in numbers. That's the input for the inverse trig functions. They're going to output or return angles, either in degrees or in radians, depending on how we interpret that. Okay, you might also see in other videos or references these functions referred to as arc cosine or arc sine or arc tangent. That's different language for inverse cosine, inverse sine, or inverse tangent. Alright, I've got some of the main points on the next page. I'm going to look at that now, and then we're going to start to work with these functions. Okay, so here's some of the main points, and there's a lot on this page. And again, I'm not going to go over every last detail, but I want you to pay attention to this equivalence that I'm going to highlight here in green. If we have y is equal to cosine theta, that's equivalent to saying that inverse cosine of y is equal to theta. Alright, so notice which side the cosine or the inverse cosine is on. And again, I'm using theta to be descriptive here. Theta is representing an angle, so the original function takes in an angle, gives you a y value or some number. The inverse cosine is going to take a number in, the y value, and return the value theta. It's also nice to look at what this means in words over here on this side. Alright, in words, the function inverse cosine returns the number between -1 and 1 to the angle in the interval from 0 to pi. Alright, so we got to pay a little bit of attention to that part right there. 0 to pi. Why? Alright, it turns out you have to restrict the cosine function to that interval from 0 to pi to make the inverse make sense. Alright, there's only one angle theta in the interval from 0 to pi, such that cosine of that angle is equal to y. Alright, and we're going to see this, and I have it written lower below, but this is going to correspond to quadrants 1 and 2. Alright, the sine function and its inverse are similar, but a little bit different. Alright, thinking about the sine function and its inverse, we have the very similar equivalence. The big difference, though, is that the domain restriction is a little bit different. So in words, the inverse sine function is going to return a number back to an angle in the interval from -pi/2 to pi/2. Alright, thinking about that in terms of degrees, that would be from -90 degrees up to 90 degrees, positive 90. Alright, again, that's going to be quadrants 4 and 1, as we're going to see here shortly. Okay, but again, really focus on left side of this line and the equivalence. That's what we're going to be doing. We're going to be bouncing back and forth between the original function notation and the inverse function notation. Similar with the inverse tangent. Okay, so looking at the inverse tangent, y is tangent of theta, inverse tangent of y therefore is equal your angle theta. So that, again, inverse trig function takes the number back to the angle. Alright, now why is this one strictly between -pi/2 and pi/2? As we saw recently in some of our work, you can't plug certain numbers into the tangent function. It's undefined, for instance, at the angle 90 degrees or -90 degrees or pi/2 or -pi/2. So that's why we have that restriction. So again, we're going to not pay too much attention to those specific details, but I just want you to realize here that the quadrant 1 and 2 is corresponding to that interval 0 to pi, and this is going to be for inverse cosine. Negative pi over 2 to pi over 2, the closed interval, that's going to be for inverse sine. The open interval, negative pi over 2 to pi over 2, excluding those endpoints, that is going to be for inverse tangent or arctangent. All right, let's get some practice working with these functions. All right, quick note before we get into some of the examples. For almost all the applications we're going to be doing using inverse trig functions, the angle that we're going to get out of those inverse functions will be acute angles. So it'll be in quadrant 1. So we won't have to, in our applications, worry so much about these interval restrictions. All right, getting on to some examples. I want to go back to the square root example for a minute here and think about that. All right, so evaluating with inverse functions, and we're in the next example, or two examples, get to evaluating with some inverse trig functions. We're going to be evaluating with those, but it's good to look at and draw this analogy to something we can kind of wrap our hands around a little bit better. All right, so we've seen that if we have the function at y equals x squared, its inverse is the square root of x. That makes sense. Those are opposite operations. Now, what if we want to plug a number into the inverse function, like 16? Well, we got a formula here, which is the square root of 16, and we know we can compute that either using a calculator or just in our head. It comes out to 4. We know that. Now, how do we do that in our head? What's the mental calculation we're going through? We're saying to ourselves here, all right, well, the square root of 16 is some number. What is that equivalent to? Mentally, we're saying, all right, that means we're looking for what number squared gives us 16. And we know by our square root property that that tells us x has got to equal positive or negative 4 by extracting square roots. Okay, the picture we had earlier in the semester, right, is if we graph the function y equals x squared, and then if we graph the horizontal line y equals 16 by setting y equal to the left hand side and y equal to the right hand side of the equation, x squared equals 16, we get 2 points of intersections. That's why we get 2 solutions. The x coordinates of these points of intersection correspond to the positive square root and the negative square root, or the opposite of the square root of 16, which gives us negative 4 and positive 4 respectively. Okay, so that's kind of a review on something we've done before. All right, but what's special about this number, though, is that 16 is a perfect square, so we can kind of do that in our head. What if we have a different number for the same function? How about the square root of 19? If I plug that into the inverse function, we can only compute that with a calculator. Mentally, we can think, yes, all right, the square root of 19 is some number, and it must satisfy that that number squared gives us 19. We can now look at it graphically too, but we have to go and plug this into a calculator, which we can do. All right, and if we did that into a calculator, I'm just going to quick do it, we would get that this is approximately, not exactly equal to, but approximately 4.3589. All right, let's look at what Desmos is going to say to us. So if I go and now graph the equation y equals x squared, and then take the right hand side and also set that equal to y, and graph both of those equations and look at where the graphs intersect, they intersect at these 2 points, right? And that's going to give us the positive square root of 19 and also its opposite, negative the square root of 19, which are the 2 solutions. Now, we're really going to be focusing on the positive solution here and kind of forgetting about that negative solution. Okay, notice for this equation, all right, and this is showcasing the equation x squared equals 19, there's 2 solutions. We are only concerned about, for this inverse function, the positive solution, only concerned about one of those. All right, let's keep that in our mind here. Okay, moving on now to inverse trig functions. How are we going to evaluate the inverse sine of 1/2? All right, it turns out we can do this with a calculator, and we will be doing that in a minute, but we can do this by hand. Also, we need to convert this from this inverse trig notation over to something kind of more familiar, like we did in the previous example with the square root and x squared. So we're saying, all right, sine of theta is 1/2. Well, let's use our unit circle for a minute. I'll flip back over to it in the notes. What is this meaning, though? We're looking for some angle that intersects the unit circle with a y coordinate, because remember, sine is y of 1/2. All right, so that means your y coordinate here must be 1/2. Well, that's a special output value for trig functions. We remember that goes with the 30, 60, 90 triangle. So this is a 30-degree angle. All right, so that's 30 degrees or pi over 6 radians. All right, so yes, that's what we're going to come out to. All right, that's going to be our answer, is pi over 6 radians or 30 degrees, depending on how the question is asked. All right, but again, looking at this equation here, there are many solutions to this equation. I've got this graph down below. If we look at the graph of y equals sine of x, and this is why in the first video we looked at that graph, and then separately the graph of y equals 1/2, we can see there's many points of intersection. I used Desmos to create this graph, and we can see the one of them that we're concerned about is right here, and the x-coordinate there is pi over 6. All right, and the y-coordinate's 1/2. So that's verifying our solution. There's other ones that work. 5 pi over 6 works, and -7 pi over 6 works. All right, and there's more. All right, some of those are other solutions to this, but the inverse trig function is only going to give us one. When we do this in Desmos, it's only going to give us one. All right, so let's use the Desmos graphing calculator now to do that. All right, I'm going to flip over to Desmos here. So I've got Desmos open. The one thing we got to do is make sure when we go over to the wrench that you're either in degree mode or radian mode. All right, I would suggest doing it in degrees first. All right, opening up the keyboard, we go to functions, and now we can see we have the inverse trig functions in this column. We want to do inverse sine of 1 divided by 2, and it's telling us 30 degrees. Okay, if we click that over to radians, it's going to give me some other decimal number which is equal to pi over 6 but doesn't tell us pi over 6. So better for us to convert this, or to compute this in degrees and then convert to radians after that. Alright, so I'm just going to take a snapshot of that, and we'll put that into the notes here. I'll do that after just to save some time. Okay, but we see the inverse sine is telling us that it's giving us 30 degrees, which you know is pi over 2 radians. Alright. Okay, I think this is just about going to be it, but one thing I wanted to do was, before we get to the next example, if we look at this picture we have of the unit circle, the handout that we gave, we can also get this information from here because we know that sine is the y-coordinate on the unit circle, so we would be looking for an angle in the first quadrant or the fourth quadrant. In the fourth quadrant, the y values are negative, so we'd be looking at quadrant 1 that has a y-coordinate of 1/2, and that corresponds to 30 degrees, pi over 6. Okay, fine. Now, what about this example? All right, inverse sine of 1/4. We could play a similar game here and say, okay, well, we know the inverse trig functions eject or return angles to us, so we're going to set it equal to theta because we think about theta as representing an angle, and then convert that over to say, well, that means sine of that angle theta must equal 1/4. This is not a common value for us, so we would have to rely on a calculator to compute this inverse trig function. And let's do that, and then I'll add it into the notes later. All right, but again, you cannot do this one by hand. 1/4 is not a familiar value off the unit circle that we've derived. So with this one, we're going to need to do, again, inverse function, inverse sine of 1/4. And notice it's not giving me a super nice angle like 30 degrees. It's giving me 14.47 degrees. All right. So we're going to come back and do a couple more examples in the last video. That's going to be it for this video, though. But again, some of these trig functions, some of these inverse trig computations, we can do by hand, or kind of see what the solutions are. Just like some square roots, we can compute, but only the perfect squares. Other square roots, we cannot. We have to rely on a calculator. Very similar here with the inverse trig functions.